So far, our programs have all been using global variables, which means we've been allocating our variables in the same low memory, meaning low number memory, in the same area as our programs are. What we're going to start doing is looking at local variables, and local variables are actually allocated up in higher memory. And it's a little backwards in that we say higher memory as we go down, but this is typically how the memory is drawn out. We start with a low zero at the top, and then we work our way down to higher memory. So anyway, so our local variables are allocated here in this stack area. So because the stack can change, the stack can be in different points at different time, meaning unlike global variables, it always starts at zero. So and our variables never move. With local variables, it depends on when they're allocated. When the function we're using is called, they can actually be in different places, so we have to handle it differently. So when we look at an actual program here, and this isn't the way we're actually going to really use it in a program. We'll look at that in a minute. This is just to look at the mechanics of how things work. But we can see here our stack pointer, which is one of our registers inside the CPU, is set at this value of FBCF. So that means right now our stack pointer is pointing right here. So at this point, the only thing we have available on the stack is this one byte above it. That's where allocation starts. So if we look at our program over here, we have what we're essentially doing is just loading some letters into the stack. So we're going to load a B into the accumulator, and then we're going to do a store byte -1 S. So that means we're going to, the S is stack relative. So we're going to look at the stack address and then store it at -1. So it's actually going to be stored one byte above it. So we can see right there we stored the B. And then we work our way through here. We have a M, so we're loading an M, and then we're going to store the M at -2. And it's at a -2 because, again, the stack pointer is pointing right here at FBCS. So -1 would be here, -2 would be there, so that gets our M up there. And then we do the same thing with the W, and which is -3. So there's -1, -2, -3. And then the third value we're storing here is an integer now. So we know that integers are actually 2 bytes as opposed to a character being 1 byte. So in this case, we're going to store it in the accumulator, or take what's in the accumulator and store it at -5, because we've had 1 byte for the B, 1 byte for the M, 1 byte for the W. Now we need 2 bytes for the integer, so that needs to go to -5. And then we finish it up here with a storing an I at a -6. So that gets us all this memory stored up here. So the thing to keep in mind is that we're using this negative value because we haven't allocated any space on the stack yet. The stack pointer is still pointing at FBCF. So as far as the system is concerned, the stack ends right there. That's where the stack ends. Anything on the stack would be below that. So the next thing we do is this sub SP command. So we sub SP 6. So we're subtracting 6 from the stack pointer. So the stack pointer was at FBCF. We subtract 6, we end up at FBC9. So the stack pointer has moved up from down here to up to here. So what we've actually done is allocated space on the stack now. So now these, whatever they are, 1, 2, 3, 4, 5 values are actually on the stack. So it's the sub SP that's actually allocating space on the stack. Once we have those values on the stack, once we've updated our stack pointer to say, yes, all that stuff is on the stack, then when we access the values, we can access them with a positive number. So now if we want to output the B, we can do a character output 5, again, using the S for stack relative. So if the stack pointer is right there, and we go up by 5, there's 0, 1, 2 because it's an integer, 3, 4, 5. That gets us up to the B, and so on through it. If we want to output the M, it's 4. So again, we start at the stack pointer, which is sitting there at FBC9. That's 0, and then plus 1 would be the 335. And since that's 2 bytes, we go up by 2 more. So there's 0, 1, 2, 3, and then we go up by 1 more, 4. That gets us to the M. So the point is, once we've allocated space on the stack with the sub sp command, once we've moved the stack pointer, that the spaces below that address now are actually part of the stack, so we can access them in positive numbers. When in the first part of this program, when we were putting things into the stack space, we hadn't allocated space yet, so we had to essentially put it above the stack. So we were subtracting values to put it up there. And again, that's not the way we do it in the real programs typically. We're usually using the positive numbers. This is just to demonstrate that before stack allocation, we're working above the stack. We allocate space on the stack with the sub sp by moving the stack pointer. Once we do that, we can use the positive values. And then finally, once we're all done, once we've done everything we need to do with the stack, we deallocate space on the stack with the add sp command. So add sp6 says, okay, we're all done. I don't have a picture of that, but that's going to take this stack pointer, move it back to where it was originally. So all these values are still there, still in memory, but as far as the program's concerned, the stack pointer is pointing back down here, which means there's nothing on the stack, so it doesn't use anything anymore. So the add sp is basically deallocating stack space. So like I said, that's kind of just the mechanics of it. The general outline of how we typically allocate and use the local variables is this way here. So here's the general steps for allocating space. We start out, we use labels with the dot equate to indicate the location on the stack. So here, if we wanted to allocate 3 variables, we'd say, all right, we're going to have an equate 0 for our first one, we're going to equate 2 for our second one, we're going to equate 4 for our third one. So those are the locations of the variable on the stack. Then we use the sub sp to actually allocate space. So the sub sp6 here actually allocates space for those 6 equates, because remember, the equate doesn't actually allocate space, and we talked about that with the comment. With the constant. The equate just puts in a label essentially that says score is being assigned to 0. So the equate says that's where I'm going to access that variable on the stack. The sub sp actually allocates space on the stack. Then once we have the space allocated, we just work the whole program as we normally would. We just use stack relative for addressing, because we're not using D for direct, because we can't go to a specific location in memory anymore. We have to go into a location in memory relative to the stack pointer. So that's what the S does. And then once we're done using all our variables, we deallocate with an add sp. So that's the general procedure. I've got a next set of slides where we'll actually walk through a program for real and see how it actually works. But this is the pretty much always when we work with a stack, we use the equate to say where the variables are. We use sub sp to allocate space. Whenever we're working with the local variables, we use stack relative, and then when we're done, we deallocate space. So that's pretty much in a nutshell how the local variables work.